in line is the topic collision. We will know about elastic and inelastic collision and will see how questions are solved from this topic. Generally, students feel difficulty while solving numericals. So today I will mainly focus on the key points, how the numericals are solved and how the equations are written in collision. So be attentive and listen carefully.
Today it's collision. What is collision? Whenever two bodies strike each other, it is called collision. So, but for physics, we will see what is collision and what are the kinds of collision and how mathematically this can be written. So, if one body strikes with another body, of course this is collision, but physically we have to categorize what kind of collision it is. It can be categorized in two ways. One is called elastic collision, the other is called inelastic collision. Now, what is collision? See, whenever collision takes place, one body exerts force on other body. If I draw it schematically here, a diagram, so that it can be represented how this collision takes place. These are the two bodies A and B. Let's consider both are moving towards each other with speeds u1 and u2. At the moment of collision, when these two bodies are in contact, at that moment, what happens? A exert a force on B. This is force on B due to A. And in reaction, B exert the same force on A. So, at the moment of collision, when these two bodies are in contact, they are exerting normal forces on each other. If we consider a system which includes both these particles or bodies, then these forces are internal to the system. And since it is internal to the system, so of course we can write momentum conservation here, because for writing momentum conservation, external force should be 0 on the system and collision takes place only due to mutual interaction. So always we can write whether it is elastic or inelastic collision, momentum has to be conserved. So we can write P initial to be equal to P final, both for elastic and for inelastic collision. Now what happens when they are in contact for that small moment of time, because forces are acting? So if we see microscopically, because this is possible that if two glass balls are colliding with each other, we cannot see that they have been reshaped. Of course, we cannot see with our naked eye, but microscopically if we see, there must be some molecular dispersion at the point of contact. So, whatever be the kind of body they are colliding, at the moment of collision, there must be some changes in the configuration of body. And this change in configuration leads to potential energy storage in that body. As far as two bodies get separated, that potential energy tries to come back again to get converted again to the kinetic energy. And then it depends if it fully recovers its change in configuration, potential energy stored is fully recovered, then it is known as elastic collision. So for elastic collision, we can write initial kinetic energy to be equal to final kinetic energy. But do remember, during collision, when collision is taking place, at the moment of contact, we cannot write kinetic energy to be equal. Even in case of elastic collision, always it should be before collision and after collision. Before and after collision, we can write, of course, kinetic energy initial to be equal to kinetic energy final, because whatever potential energy is stored during the moment of collision, that gets fully converted to kinetic energy in case of elastic collision. If it is not at all gets converted into the kinetic energy, whatever de-shaping has been there during collision remains like this only, then it is called a complete inelastic collision. So here kinetic energy initial is not equal to kinetic energy final. Though I can tell you that no collision in universe is completely elastic or completely inelastic. Always it has to be partial, somewhat elastic, somewhat inelastic. If it is much closer to elastic, then it is known as almost elastic collision. If it is much closer to Inelastic, it is known as inelastic collision. You can take example of if two steel balls are colliding, then of course we will say, because we cannot see that after collision takes over there has been any change in shape, that is change in configuration for the ball, and we will say that kind of collision is elastic collision. If two mud balls are colliding, then it will be D-shaped and will remain like that only. So then that can be termed as almost like inelastic. So this is how we can differentiate between elastic collision and inelastic collision. But do remember that momentum conservation can be written for both the kinds of collision. One more thing is there, which though I will introduce later in this session, that is called coefficient of restitution. Later I will explain in detail what this thing is. Value of that coefficient of restitution should be 1 if it is perfectly elastic and 0 if it is perfectly inelastic. Though for all practical collision, E lies between 0 and 1. So it should be in the range of 0 to 1 for any practical collision. Now after knowing what kind of collision is elastic and inelastic, we can go into some mathematical details to solve a numerical. So first let us consider if elastic collision is taking place in one dimension. The two bodies are moving in one dimension only, then how the situation can be solved. Let's consider the case two bodies I have taken, let that be A and B. Both are moving with velocities v1 and v2. And if after collision this A gets velocity v1 dash and B gets velocity v2 dash. Here you can see these are moving in same direction, and for collision to take place v1 should be greater than v2 initially. Now if these two bodies are colliding, then first thing that we have to write, always whatever be the kind of collision, the first equation we have to write is momentum conservation. So we will write m1 v1 plus m2 v2, which is momentum of system before collision, has to be equal to momentum after collision, that is m1 v1 dash plus m2 v2 dashed. Or if we solve it a little, it can be written as m1 v1 minus m1 v1 dash is equal to m2 v2 dash minus m2 v2, or m1 v1 minus v1 dash is equal to m2 v2 dash minus v2. So this is momentum conservation before and after collision. Now here we are considering our collision to be fully elastic. So we can write kinetic energy also to be same before and after collision. That will give half m1 v1 square plus half m2 v2 square to be equal to half m1 v1 dash square plus half m2 v2 dash square. Or if we take m1 as common, then it can be written as v1 square minus v1 dash square to be equal to m2 v2 dash square minus v2 square. Let this be our equation number 2, and the first equation we had got be 1. From first and second equation we can now write v1 plus v1 dashed to be equal to v2 plus v2 dashed, or v1 minus v2 is equal to v2 dash minus v1 dash. Now you can see this is very important thing, v1 minus v2. What is this? It is the rate at which separation of the body decreases before the collision. So this is known as relative velocity of approach. It is known as relative velocity of approach, because with this rate the separation between the bodies are decreasing with time before collision. What about this other term? This can be written as, because it is v2 dash minus v1 dash, so with this rate separation is increasing with time after collision. So this is known as relative velocity of separation. From here we can conclude one more thing, that if collision is perfectly elastic, then relative velocity of approach before collision has to be equal to relative velocity of separation after collision. Now if we solve it further, finally we will get v1 dash to be equal to m1 minus m2 v1 upon m1 plus m2 plus 2m2v2 upon m1 plus m2, and v2 dash to be equal to 2m1v1 upon m1 plus m2 minus m1 minus m2 v2 upon m1 plus m2. So these are the velocities we obtained after collision if collision is perfectly elastic and in one dimension. Now we can discuss some special cases based on these results. If elastic collision is between a heavy body and a light body, it is the first special case I have considered. So what these values will be then? If we solve, m1 is much greater than m2, then of course we can write m1 minus m2 upon m1 plus m2 to be equal to 1, and 2m2 upon m1 plus m2 to be equal to 0, because m2 is negligible. And on considering these two situations, we can write v1 dashed will be equal to v1 and v2 dashed will be equal to 2v1 minus v2. So the heavier body continues to move with almost the same velocity, and if the lighter body was kept at rest, that is v2 is 0, then lighter body after getting a push from the heavier body will fly away with a velocity double the velocity of heavier body. If previously it was at rest, v2 was 0. Now if we suppose that m2 is much more than m1, then a light body is hitting a heavy body. In this case, we will get m1 minus m2 upon m1 plus m2 to be equal to minus 1, and 2m2 upon m1 plus m2 to be equal to 2, and 2m1 upon m1 plus m2 to be 0. So final velocities now can be written as v1 dash to be equal to minus v1 plus 2v2, and v2 dashed is equal to v2. That is, the heavier body continues to move with almost the same velocity, and velocity of lighter body changes. If heavier body were at rest, that is v2 is 0, then v1 dashed is minus of v1. So the lighter body returns after collision with almost the same speed. This is the case you can consider when a ball collides elastically with a fixed wall and returns with the same speed. The next special case is elastic collision of two bodies of equal mass. So if we substitute m1 is equal to m2 in the expression we had derived earlier, we will get v1 dashed is equal to v2 and v2 dashed is equal to v1. What does it mean? That when two bodies of equal mass collide elastically, their velocities are mutually interchanged. One has got velocity of second and second has got velocity of first. So this will be very useful while solving numericals. Whenever you see in a numerical bodies to be colliding are having same mass, we can simply exchange their velocities after collision. Now we have to consider perfectly inelastic collision in one dimension. This time it is inelastic. So we cannot write kinetic energy before the collision to be equal to kinetic energy after the collision. But of course we can write momentum conservation here as well. So we got m1v1 plus m2v2 to be equal to m1 plus m2 multiplied with v. Now what is this v? V is the common velocity with which the two bodies after collision will move together, because if it is a perfectly inelastic collision, then relative velocity of separation should be 0, and if it is 0, of course two bodies will move as a single system. So I have taken that common velocity to be equal to v. Now if we solve it, v will be get as m1v1 plus m2v2 divided by m1 plus m2. This time we cannot write kinetic energy to be equal before and after collision, but of course we can calculate loss in kinetic energy. So before collision, kinetic energy is half m1v1 square plus half m2v2 square, and after collision this value is half. Now the both is moving as a combined system, so directly we can write half m1 plus m2 v square. What is change in kinetic energy then? Write kinetic energy final minus kinetic energy initial. That will be equal to half m1 plus m2 v square minus half m1 v1 square plus half m2 v2 square, which is equal to, if we take half common outside the bracket, that will be m1 m2 taken common v1 square plus v2 square minus 2 v1 v2, and this whole divided by m1 plus m2. On further solving, it will come to m1 m2 v1 minus v2 whole square. As you can see here, this is v1 square plus v2 square minus 2 v1 v2. So it can be written as v1 minus v2 whole square. This divided by m1 plus m2. This is the loss in kinetic energy if it is a perfectly inelastic collision, but that one in one dimension only. Now we can completely understand what is coefficient of restitution, because this can be defined as relative velocity of separation upon relative velocity of approach. This is how we can define coefficient of restitution. And as I had discussed earlier also, that for a practical collision, this E should be in the range 0 to 1. Never it can achieve 0, never it can achieve 1. It has to be in this range. If we consider elastic collision in 2 dimensions, because you will get questions for 2-dimension collision also, then of course we can write energy conservation as we had written in earlier case, that was half m1 u1 square plus half m2 u2 square should be equal to half m1 v1 square plus half m2 v2 square. But while writing momentum conservation, now we have to consider their directions also. So if you consider the directions, if collision is taking place in xy plane, then separately we have to write px initial to be equal to px final, and in y direction as well, py initial is equal to py final. This will give you 2 separate equations that will include of course theta also, because if these 2 bodies are colliding, one is moving in this direction, other is moving in this direction, and this is the line of separation. So let angles are theta 1 and theta 2, then we have to write p1 cos theta 1 minus p2 cos theta 2 is equal to whatever be the final conditions. We can write like this. It has to be always in x and y component, and then we can solve these 2 equations along with energy equation to get the final result. It cannot be a generalized result for 2 dimension, because it depends on a number of things. It depends on whether one body was at rest before collision or when other was at rest, or what were the angle with line of separation. So it depends on a lot of things. Directly we cannot write any generalized result. What you have to remember is, you have to write energy conservation and then momentum conservation in both the direction if it is taking place in a plane. If it is for a 3 dimension, then you have to write in z direction as well. So just do remember all these concepts, key points in your mind, and then you can start solving numericals. Let us consider one example more. A ball moving with velocity 2 meters per second collides head-on with another stationary ball of double the mass. If the coefficient of restitution is 0.5, then their velocities after collision will be. Different options are provided here. So let us start solving the numerical. As we know, coefficient of restitution we can write as this to be equal to v2 minus v1 upon u1 minus u2, where u1 and u2 are initial velocities and v1 and v2 are final velocities of 1 and 2 respectively. Also from the law of conservation of linear momentum we can write m1 u1 plus m2u2 to be equal to m1v1 plus m2v2. So v1 will be having value. On solving these two, we are going to get m1 minus em2 upon m1 plus m2 whole multiplied with u1 plus 1 plus m2 upon m1 plus m2, this whole to be multiplied with u2. On substituting the numerical values, u1 is given 2 meter per second, u2 is 0, m1 is m and m2 is 2m. Also E is given 0.5. So we will get finally v1 to be equal to m minus m upon m plus 2m multiplied with 2. That will be equal to 0. And what about v2? If we substitute the values for expression of v2, which is 1 plus E m1 upon m1 plus m2, this whole to be multiplied with u1 plus m2 minus E m1 upon m1 plus m2 to be multiplied with u2. This expression also has come from solving the first two equations, and now on substituting numerical values, we will get v2 to be equal to 1 meter per second. So our correct option is 0 and 1, which is option number 1. One illustration I have taken here, in which a block of mass m0 is held at rest on the smooth inclined plane by the stop block at A. The bullet of mass m is traveling at speed u when it becomes embedded in the block. Okay, we have to solve a number of things. First, for collision between block and bullet, we have to write which of the conservative law can be applied. This is between bullet and the block system. Now, what conservation law can be written here? Can it be conservation of mechanical energy, or linear momentum along horizontal, or conservation of linear momentum along vertical, or linear momentum in a direction parallel to the inclined surface? So you have to choose among these 4 conservation laws which can be applied here. Let us analyze each of this. Can it be conservation of mechanical energy? Here the block is not free to move along horizontal or vertical direction. It can move only along the inclined surface when the bullet collides. Jerk or impulse of course, jerk or impulse will be provided by the inclined surface. So we cannot write conservation of linear momentum in horizontal or vertical direction. Of course, we can write this only along the incline. So along the incline we can write momentum conservation. Energy conservation also here cannot be written, because for energy conservation work done by external force should be 0, though here different external forces are acting on the block. So we can only write conservation momentum, that is P to be constant along inclined surface. In next part, it is asking in which direction net impulsive force on the system is 0. Let us see. As just now I have discussed, the impulse by inclined plane will be along normal. Always when two surfaces are in contact, the interactive force has to be along the normal. So impulsive force between bullet and block will be internal, and net impulse will be along normal to the incline. So for the net impulsive force, we can write it has to be along the normal to incline. For third one, what is the impulse generated between the block and the inclined plane? By impulse momentum theorem, we can write, if impulse I am denoting by I, then it can be written as change in momentum. Now, if I write along the normal, Pi can be written as minus mu sine theta. Can you see this? Let me draw the situation here. This is the direction of u and it is the angle. So along the incline it can be written as, so along the normal it can be written as minus mu sine theta, and P and P final in this direction is equal to 0. So in direction of normal, we can write change in momentum as P final minus P initial, that is equal to mu sine theta. So we got impulse between the block and the inclined plane is equal to mu sine theta. This is our result for third part. With this, now the collision is complete, but in next session we will see some more illustration so that you will be able to solve numerical if it is given from this concerned portion. Till then, goodbye.